Hello, my name is David Waltzman and I'm a Simulation Division Manager at GoEngineer. Today I'm going to walk you through our SOLIDWORKS Simulation Symposium and explore the variety of simulation tools that SOLIDWORKS has to provide. We'll start off looking at two flow simulation cases, and then into two finite element cases, and ending with our plastics tool. The first application we're going to be looking at is a variable area flow meter. You can see that there's a tube, varying diameters, and a float inside, and the position of that float is going to show us different flow rates and pressures inside of our product. So we'll start off with looking at the initial setup, move on to the calibration, and then look at some particle flow. The tube tapers down, as I mentioned, with the float inside. We have the fluid inlet coming up from the bottom there. So what we want to know is what float position corresponds to a given flow rate. Looking at a basic force balance here, we see that we have the force of the fluid, we have buoyancy, and we have the weight of the float. It's always important to do a quick gut check of your analysis to make sure that everything's set up properly. In SOLIDWORKS Flow Simulation, we're simply going to define a pressure at one end, that's environmental pressure, and then an inlet volume flow from the other end. We set goals in SOLIDWORKS Simulation for outputs that we want from our analysis. This serves a dual purpose. One is for those values to converge, the second is for that easy readout. Because there's going to be areas of refinement that are necessary in this model, we could define a local initial mesh over the volume of that cylinder. So the cylinder will be a fluid volume in the analysis, but allows us to crank down the size of our cells to still maintain accuracy. In SOLIDWORKS Flow Simulation, we have the capability to add in solution adaptive meshing. With this approach, as the simulation's iterating, SOLIDWORKS is monitoring the trends and refining the elements in areas of high gradients. In this scenario, we'll be refining it in areas where there's turbulence or some vortices that are generated on the back side of our float. We get great two-dimensional outputs like streamlines. This is a 2D cut plot. We can also look at 3D flow trajectories as well. Here's a closer look at the backside of our float. One of the important outputs that we're looking at is drag force. Here we see how that value is changing in time. Again, SOLIDWORKS Flow Simulation has an iterative solver, so we see how the value bounces around, stabilizes, and once it stabilizes, then the simulation is done. Now let's use a goal optimization in our parametric studies to look at our force. So we can see for our target value of 0.04 pounds that at 100 millimeter displacement, we're getting 0.0473. If we move to the other range of our tapered tube at 60 millimeters, we're getting 0.02. And so now we try places in between to try to hone in on our target value. So we try a couple more times, and we end up with 0.04 right on the nose, 92.53 millimeters. This is a value that may not have been immediately obvious to us. So by implementing a tool like SOLIDWORKS Flow Simulation, we're able to get right in on the results that we're looking for. We can, on the post-processing end, inject particles into our study. The condition for these particles is that they're not disrupting the flow of the fluid. So we'll introduce sand here. You can say how many particles, the diameter of them, the density is necessary, and the mass flow rate, so you know how many of these particles are being introduced. We can even look at effects of erosion on the float as well. Now let's look at a CPU enclosure design. This enclosure is filled with a variety of electronic components mounted on a PCB. There's also some openings as well, so we can investigate if we want to have any fans on those openings. Or on the tops, do we want to have vents there? Or is that not necessary to have? Either way, our objective is to minimize the heat buildup and stay under the maximum threshold temperatures for our various components. The first design decision to look at is whether to vent or not. To vent seems like the better option off the bat, right? You're going to have natural convection, taking the heat out. But this adds more cost to the mold. It also weakens the case as well. So imagine if you set some books on top of it, right? Is it going to dip down and possibly damage the product? Using SOLIDWORKS Flow Simulation, we're able to run studies with both scenarios. We simply just clone the project and apply it to a new configuration. And we can see that while there is a difference in temperatures for our CPU, IC package, and RAM module, they're both below the threshold for those respective devices. Furthermore, we should go with the less expensive, more mechanically robust design without the vents. The next decision to make is whether to have fans be inlet or exhaust fans. And do we need all three, or can we get away with one or a variety of combinations of two fans? Here we're looking at all the different scenarios for an inlet fan. So we look at the A, B, and C position, and then combinations thereof. What's interesting to note here is that the heat island locations change significantly based on the locations of the fans. But again, what's important isn't the region that's hot, but if those temperatures exceed our thresholds. Now let's look at the outlet fans. We can see in comparison to the last slide that this looks quite different. Again, here we're sucking the hot air out. Looking at our inlet fans, we see that there's some combinations that don't work. For example, if we're looking at the red bar under CPU, we see that's exceeded. The green's exceeded. Our teal's exceeded. But the rest of them are good. Now if we go into the IC package, we see that now the purple is too hot. And regardless of the configurations, it looks like our RAM was kept under temperature. Looking at the outlet fan results now, it's immediately obvious by looking at the IC package that all the temperatures are hotter than the allowable limit. Therefore, it's much more effective to blow cool air in than suck the hot air out. In summary, here's all of our different possibilities for the inlet fan. And of those, there's 3 that satisfy every condition. And from those 3, combination B and C is the most productive, and that it keeps the temperatures the lowest on each of our components. Now let's investigate a finite element analysis example. So we've been looking at computational fluid dynamics, at fluid flow and heat transfer. Now we're moving on to mechanical simulation. Here we're looking at a skid. So this is a mobilized piece of equipment. Here we have some pumps, we have ladders, all types of heavy machinery that's delivered on a structural frame, then implemented in series with a variety of other devices that are on skids. What we want to do in SOLIDWORKS simulation is utilize effective boundary conditions to reduce this simulation to just the structural frame. We want to reduce our model down just to the structural frame so that we can solve it more efficiently. We're also not interested in what the pump looks like or the other heavy objects. We just want to know its effect onto our structure. We'll start off by looking at the strength and frequency, then we'll optimize the skid plate design, and finish off by adding the pump into the mix and see how, when it's in operation, how it affects the structure. We have a variety of pumps and motors and pipes that altogether weigh 34,000 pounds. Our pumps are operating at a range of 600 to 3,600 RPM. We'll take that into account for the harmonic analysis. The weight, though, is going to be directly relevant now for a static analysis to see, is this product going to bend too much? To assume the rest of those structures, we created a remote load. That's what we're seeing in magenta, and we're going to apply it to the 2 sheet metal faces that are supporting all of that load. In SOLIDWORKS simulation, we call this a remote mass. So it's still using the center of gravity of all that weight, but now applying it to those faces. We also enter in gravity, which is our large red arrow pointing down, as well as fix our 4 corners with a fixed geometry end condition so that they don't move. You may notice that our skid design now looks like a series of blocks. That's because in SOLIDWORKS simulation, structural members created using the weldment tools in SOLIDWORKS are automatically created as beam elements in a simulation. We also have a shell mesh for our sheet metal plates that's also automatically converted upon meshing. Finally, we define our material as carbon steel so that we can see how stiff it is. Looking at the results from there, we see stress, displacement, as well as factor of safety. Right, so there's probably going to need to be some improvements to the design. We see how the asymmetries in the model lend themselves to a little twisting. So now let's look at the effects of the pumps. In order to do that, we're going to run a linear dynamic simulation, which has a frequency study embedded inside of it. With the frequency study, we have the same loading conditions, but now instead of stress and displacement, we get the resonance of our model, so what frequencies excite the geometry, as well as their mode shapes. And what we do in the linear dynamic study is include as many of these mode shapes as needed to accurately characterize all the possible movement of the structure. This also encompasses the full operating zone of our pumps and motors. So our first challenge is to reduce the sheet metal thickness. Criterion is that max deflections less than 0.6 inches, and a factor of safety greater than 2. And our objective is to maximize our first natural frequency and to minimize the mass. Again, without analysis, this would be very difficult to do, but since we're modeling everything in 3D, we're able to see the effects. Setting it up an optimization study in SOLIDWORKS Simulation has three components. There are variables. These can be model dimensions or simulation parameters. Then we have constraints, which are created from sensors in SOLIDWORKS. If you've never used a sensor, I highly suggest checking those out. So we'll be looking at the max displacement and factor of safety in our model and creating rules for that. And once SOLIDWORKS obeys all those rules, we want to choose the one that has the least mass and the highest natural frequency. So all of that's in our one screen. We hit run and we let SOLIDWORKS worry about the rest. Here we can see there was 9 design iterations and that SOLIDWORKS found the optimal one. So all the iterations that are listed in gray satisfy the constraints. All the ones in red violated a constraint, and the specific violation is in a dark red. And then SOLIDWORKS highlights the optimal solution from all those gray ones in green. So we see here the weight of our initial design to our final design saves about 27%, and that we also increased the natural frequency 1.2 hertz, which seems like a very small amount, but if you look at it relative to the initial 10.4, that's actually an 11% increase. It's quite significant. So now, again, we're going to be applying those same conditions, but extending out to the harmonic analysis. This graph here is looking at several data points on the model, but what we can see are two fairly large spikes. One at 13 hertz and one at 20 hertz. This is important data because it's showing how our structure responds to a specific excitation. So we definitely want to avoid those two peaks as well as any of the space in between them. So if I was a betting man, I would want to avoid somewhere between 5 to 25 hertz and really live beyond that where there is relatively no response. Now let's look at a swaging tool and the nonlinear capabilities inside of SOLIDWORKS Simulation. We'll go through the setup of a nonlinear analysis, investigate the results, and then make a design change. There's several sources of nonlinearities in the FEA model. The first one are geometric nonlinearities. The way we characterize this is by a significant change in shape. There's not a quantitative value for this, but imagine you have something flat and it's held at one end and something's pushing down on the other, and eventually it becomes a U or an L. Well, that shape is dramatically different from the beginning, and it's going to yield different results. So in a linear simulation, SOLIDWORKS calculates the initial shape of the object, defines a small load, and then keeps applying that load to get your final deformation. In a nonlinear study, there are calculation steps, and after SOLIDWORKS deforms the part a little bit, it recalculates the shape and applies the load again. This is a much more accurate process, and realistic for that matter. We can also take into account material nonlinearities. So in just a linear static simulation, you're looking at a linear elastic material model, meaning that you have your Young's modulus, and you assume that as far as you push the product, it's going to snap right back. It always stays in the elastic region. It never passes yield. But now in a nonlinear analysis, since we're looking at time steps, we're able to apply various material models that have curves in them associated with the strain. So whether it's a hyperelastic model for rubber or a shape memory alloy or a viscoelastic, we can now apply the correct material model. The last one we'll look at here is contact nonlinearities. So as things come together and slide, that's going to be changing the shape, and as such is going to affect the response. So let's look at our initial design. We have one face that's fixed, and then we have our swaging tool, which is pushed into the pipe. Now I'm not quite sure how much pressure is needed to push it into the pipe, but I know that it needs to go in 4 inches to perform. So in SOLIDWORKS Simulation, we can actually apply a displacement as a load. So we have our tube and our tool. It's necessary for the design that our tool be much more rigid than our tube, since it's going to be used to open it up. Metals use stress-strain curves to characterize their material properly. So here we can see that if we had just estimated this from a straight line, it would not be accurate at all. So since we know it will be going past yield, because that's the point of this tool, we definitely want to go with our stress-strain curve. Since our geometry is the same all around its center axis, we can use a 2D axisymmetric simplification inside of SOLIDWORKS Simulation. In this scenario, we're only going to need to apply triangles on our 2D slice. This will run much, much faster than if we had our whole 3D solid filled with small tetrahedrals. So this is purely a productivity tool that we give you inside of SOLIDWORKS. As I mentioned, we enter in our stress-strain curve. We'll go with a plasticity model. So we know that once we go past our yield stress, there's going to be some plastic deformation. We need to define a no penetration contact between the surfaces where the tool and the tube are going to meet. Even if they're not initially touching, as the product's moving in, there's going to be contact and sliding. So we need to define no penetration. And again, this is a benefit of the nonlinear analysis, is that once they make contact, we'll be recalculating the stiffness of the model. Since we expect a significant amount of deflection, we're using our large displacement formulation as well as our large strain option. Here's what the results look like. As we start pushing in, we see that there's some stress, and then there's a huge leap in our response graph, and then it levels out somewhat again. So why would that happen? Well, we're looking at 3 different points along our tube here, and you can see that really steep section is where the product buckles. So we've by no means yielded the material, but as it's changing shape, it became significantly weaker and just popped out. This is one of the phenomena, right? It's called buckling, and we're able to see it in a nonlinear analysis. In a linear static, we would have missed this and need to run a linear buckling study as well. But again, from all the contact that's happening, really the nonlinear is the best way to go. So let's make a design change and see what happens. All right, so here we're able to see that there is some buckling, but you see how it exists just at that point? And again, in our response graph, we see that it's staying pretty low, linear, and then it just shoots up. So the advantage of implementing a software like SOLIDWORKS Simulation is that you're able to dig into your current designs and any new designs and explore the effects before lunchtime instead of waiting, going through ECOs, approvals, manufacturing, testing, and then finding out that something's wrong with the product. We'll finish off today by looking at our SOLIDWORKS Plastics. That's the injection molding simulation software. We'll start off with looking at the fill of a single part, then move on to a family mold and look at the cooling of the mold. As far as the setup goes, SOLIDWORKS Plastics is fairly intuitive in that we're stepping through the process parameters of a manufacturing process. What's different from the last 2 packages that we looked at that were defining environmental loading, this is all manufacturing. Right? So a little different mindset. We'll need to define how long it takes to fill the plastic, what the temperature of the mold is, what's the plastic that we're using, where does it come in. We've seen that we've defined a gate at the bottom of our part here, and that plastic is going to fill in from there. But we'll want to know things like, are there short shots or air traps or weld lines or sink marks? How much is it going to move? These are all great questions and things that we can answer in our plastics package. The result that most of us want to see right away is how it fills. This is a chart of time and showing that it makes sense that the opposite end will fill last. What's nice is that we can animate all this as AVIs and send it out as presentations. Moving on from a single cavity, we're able to explore family molds and multi-cavity molds. So whether the parts are identical or not, we can lay them up and then use sketches in SOLIDWORKS to create the 3D path of the sprue and runner system. From there, we identify diameters for each of the line segments, and that'll simulate our plastic flowing through that system to our cavities. Again, with our filling results, we see how the plastic spreads, and if we have enough injection pressure to do that effectively. I mentioned that we can build molds. Sometimes we have more information, sometimes we have less. In this case here, I happen to have my cooling line layout as well. So we could define the water coming in and the temperature and the flow rate and see how that reduces the hot spots on your parts. Again, this is great flexibility because we can explore several configurations of cooling lines before going into production and get the best results we can up front. Reduce those iterations, reduce the schedule, reduce the cost. It just makes sense to do all around. We've covered a lot of information today. Hopefully you're able to learn quite a bit, but I hope you want to know even more, which is why I'm introducing here GoEngineer, which is our GoEngineer knowledge base. So if you hop onto our website, we have thousands of pieces of content from SOLIDWORKS and our technical staff here at GoEngineer. So I highly recommend for you to check those out, as well as contact your local application engineers to learn more about the product. This is David from GoEngineer. Thank you for tuning in.